We're talking about linear programming. We want to graph systems of linear inequalities to find the solutions of the system, solve linear programming problems. So in this case, we want to focus on maximum and minimum values. So we're given 6 constraints. And the first thing is we want to graph those constraints. So the first two, x is greater than or equal to 0, y is greater than or equal to 0. When we go to our graph, that's the x-axis and the y-axis. So this one would be x is greater than or equal to 0. So we want to be in this direction, and this will be y is greater than or equal to 0, and we want to be in this direction here. The next one we have 2x plus 3y is greater than or equal to 6. And 2x plus 3y is greater than or equal to 6. So if x is 0, in this case, if x is 0, then y has to be 2. So if x is 0, then y has to be 2. And if y is 0, then x has to be 3. And then we can shade that line that goes through those points, and we can see that we have a slope going down 2 over 3, down 2 over 3, up to back 3, up to back 3, and we can draw that line. And that was the equation 2x plus 3y is greater than or equal to 6. And if we substitute 0, 0 in, these both go to 0. Is 0 greater than or equal to 6? No, it's not. So we can shade that way. Okay. The next one we can look at is 3x minus y is less than or equal to 15. So for that one, if y is 0, then x has to be 5. So we'll put our scale back on our graph. So here we have 5. Here we have negative 5, negative 5, and 5. And so for this one that we were talking about, if y is 0, x is 5, and if x is 0, then y has to be negative 15, which will be pretty far down. But if we were going to solve this, we know that the slope is going to be negative 3. So we can go, it's going to be positive 3. So we go down 3, back 1, down 3, back 1. And then we'll have that graph there. So then we have, that's the graph of 3x minus y is less than or equal to 15. And if we substitute in 0, 0 for that, we get 3 times 0 minus 0 is less than or equal to 15. And that is true because 0 is less than or equal to 15. So for this line, we want to be on that side over there. The next one that we have is negative x plus 4 is less than or equal, or excuse me, negative x plus y is less than or equal to 4. So if y is 0, x has to be negative 4. And if x is 0, y has to be 4. So we have that graph that goes through those 2 points with a slope of 1. And we have to be on this side. And then we have our last one, 2x plus 5y is less than or equal to 27. And that one, off the top of my head, I can't do that one, so I'm going to have to solve that one. And so I'll write it right here. 2x plus 5y is less than or equal to 27. Subtract 2x. And we get 5y is less than or equal to negative 2x plus 27. And divide by 5. And then we get y is less than or equal to negative 2/5 x. And that's 27 over 5, or 5 2/5. So 5 2/5, a little bit up there. And we go down 2/5. So we end up right there. And then we go down 2 over 5. And we end up right there. And then we have the line that goes between them. So this is the 2x plus 5y is less than or equal to 27. And if we check 0, 0, 2 times 0 plus 5 times 0 is less than or equal to 27. And that is true. So we want to shade that side. One that we did forget to check. We have this constraint here. Probably going to shade on this side, but I just want to write it out just to make sure. So we have negative x plus 4y, or plus y, is less than or equal to 4. So we're going to check 0, 0. So 0 is less than or equal to 4, and that is true. So then we want to shade this side of that line, and we see our feasible region is right here. And so, whoops, a little bit outside there. So there's the feasible region in the middle, and then we can see all the vertices that we have to check. So we have 3, 0. We have 5, 0. We have 6, 3. We have 1, 5. We have 0, 4. And we have 0, 2. So we have 2, 3, 4, 5, 6 to check and see what we have there. So our objective function is a function n evaluated at the coordinates x, y, which is equal to 100x plus 40y. And so we'll substitute those coordinates in, and we'll see what we get. So we have the function n evaluated at 1, 5. So that is going to be equal to 100 times 1 plus 40 times 5. And what we get is 300. So then we want to check this 6 times. So we have the function. We're going to evaluate it at 100. We're going to plug a value in. And then so for this case, we want to check 0, 4. So 0 for x, 4 for y. And we get 160. Then we want to check the next one. We have the function n evaluated at, we want to do 0, 2. So that's going to be equal to 100 times 0 plus 40 times 2. And in that case, we get 80. And we have 3 more to check. So we have the function n evaluated. So the function n evaluated at 3, 0. And we get 300. So then we have the function n evaluated at 5, 0. Forty times 0, 40 times 0, 0. So then we get 500. And then the last one we have is the function n evaluated at 6, 0 or 6, 3. And for that one, we get 720. So we can check. We have the max at 720, and the minimum is at 80. Now some of these we probably didn't have to check if we think about. Do we have to check 0.4 if 0.2 is a point? Automatically, because they have the same x, and this one has a smaller y in this case, we know that this one's going to be smaller. Do I have to check 5, 0, and 6, 3? Well, this one is bigger, has both x and y coordinates bigger than this one. Has both x and y coordinates bigger than this one. So I automatically know that this one's going to be bigger than these two, and probably bigger than these two, but because the 5 is a lot bigger than the 3, you might have to check that depending on the weight of each constant.